Hi everyone, this video is entitled Similarity, and we've been using that term the last couple sections. And we said that similarity, if two things are similar, they are the same shape but not necessarily the same size. Alright, and in this little video, in this little section, we're going to be a little more precise with how we say two things are similar, and we're going to define it as what's in this box here, which is on your packet. It says two figures are said to be similar if one can be mapped onto the other using a dilation followed by a congruence. And remember, a congruence is a sequence of basic rigid motions, meaning a sequence of translations, reflections, or rotations. Alright, or I can do the congruence first, the translation, reflection, or rotation, and then follow it by a dilation. Alright, so in exercise 1 here, we have two triangles on this coordinate plane. It's really just quadrant 1 of the coordinate plane, and we'll label this over here. This is going to be x, and this is going to be my y-axis. Alright, and what I want to do is look at these two triangles and do two things. First of all, are they similar? Alright, and remember, if they're going to be similar, they have to have the same shape, but not necessarily the same size. Alright, and it looks like these are the same shape. They're both right triangles, but they're definitely not the same size. So first of all, we're going to say, well, yes, they are similar. And in order to prove that, we have to do this part as well, though. We can't just kind of guesstimate. We can't just kind of say, oh yeah, they look about the same shape. We have to describe a dilation and a congruence that is going to map one to the other. Alright, so let's do this. Let's do it this way. If we start with this big triangle, and I simply count how big these sides are, I can count this one on the right. I can start up here at the corner and say, well, 1, 2, 3, 4, 5, 6. So that right hand side is 6 units long. And if I count the bottom side, I can start at this corner and say 1, 2, 3, and that bottom side is 3 units long. And this is just kind of like setting things up to see if I can actually do a dilation and change it to be this size. Well, if I count here, this is 1, 2 units. Okay, so I would need to change that side that is 6 units into a side that is 2 units. Alright, and this one along the bottom, which would match up with this one, alright, is actually just 1 unit. So at first, I'm just kind of taking a look to see is there possibly a dilation that could occur. And if I multiply 6 by 1/3, then I get 2. And if I multiply 3 by 1/3, well, I get 1. So it looks like there's a possibility that there is a dilation that I could do to change this big triangle into this small triangle. Now I could do it the other way. I could start with the small triangle and change it into the big triangle. That'd be maybe a little easier. That'd be multiplying by 3. If I started with 2, I can multiply 3 and get to 6. But either way is fine. So it looks like there definitely is a dilation that will change these triangles to be the same size. Alright? I'm going to write down the coordinates of the points. I'm going to label these points and then write down what they would change to if we did a dilation. Okay, this is going to be A prime, B prime, and C prime. Okay, and so here's these 3 points that I'm going to start with, the big triangle. And if I multiply each one of these by 1/3, well, then I get these points right here. This is going to be 2, comma 3, and this is going to be 2 comma 1, and this is going to be 1 comma 1. And I'm gonna graph these in red, so they would end up here, here, and here. Okay, now we've gotten the triangle to be the same size. If you compare this red one and this little one we're trying to get to, theirs would be the same size. But then how do we get it to be right on top of each other? Well, they're oriented the same way, and if I had them oriented the same way, I could simply do a translation on each one of these points to move them up to the top here. So if I count, if I start here and I count 1, 2, 3, 4, 5, I'm going to go to the right 5, and I'm going to go up 1, 2, 3, 4, 5, 6. So if I do a translation of 5, comma 6, then let's see what points each of these turn into. I'm going to add 5 to every one of the x values, and I'm going to add 6 to every one of the y values. Okay, so I added 5 to each one of these, and I added 6 to each one of these, and I get these points right here. And if you compare them, well, A is over 7 and up 9, so that is this point right here. And B is over 7 and up 7, so that is this point. And C is over 6 and up 7. Alright, so what I did was I proved two things. I proved that I could change this big triangle to be the same size as this small triangle by multiplying by a third, or, well, and I should say, and I took this triangle and I translated it to the right 5 and up 6, and that brings me right to this triangle A prime, B prime, C prime. Okay, so those are the things that I'm going to be expecting you to be able to do, is tell me if they are similar or not, and if they are similar, well, what dilation, and then what translation, reflection, or rotation will get us to that second triangle or whatever shape we have. Okay? Alright, here's exercise number 2, and a little different notation for you to be aware of here. First of all, this little symbol right here, it looks like a triangle, so it stands for triangle. So if I were to read this little section, I would simply say triangle ABC. Alright, another little piece of notation is this little squiggly right here, and this simply means similar to. Okay, so whenever you run into this symbol, you just want to substitute in the word similar, or the words similar to. Alright, so I would read this as triangle ABC is similar to triangle XYZ. Alright, now in this exercise, they're telling you that from the get-go. They're telling you that these two triangles, and we're going to label them in a minute, these two triangles are, in fact, they are similar. So that means they are the same shape, and they are, there's a dilation and a congruence that you would allow you to map one to the other. Alright, so let's do this one a little different. Let's start with the smaller triangle and see if we can map it through a dilation and a congruence to the other. So I'm going to go ahead and label these, and then we'll pick it up here after I get that done. Alright, as you can see, I have the points on the triangles labeled, and I have the actual coordinates of triangle ABC here. And what I want to do is figure out what dilation I would need to do, and then what congruence I would need to do to map ABC, triangle ABC, to triangle XYZ. Alright, so first let's tackle the dilation. And what I'm gonna do the same thing as I did in the previous exercise to kind of give me an idea of what dilation I think it is. So if I just simply count side AB, well, that's 1 unit long. And if I go up here to its matching side, side XY, that is 2 units long. So right away, I'm saying, well, if I multiply this 1 unit by 2, well, it's going to make it equal to 2 units. So let's check and see if it would work over here. This side BC would be 3 units long, 1, 2, 3, and this side, which would match up to it, would be 1, 2, 3, 4, 5, 6 units long. Again, if I multiplied 3 by 2, that would give me the right length. So it looks like my scale factor here is going to be r equals 2. Alright? I could do a similar thing if they were already lined up with using the coordinates, but this works right now to figure out my new coordinates. So I'm going to do the dilation on ABC, and when I multiply each by 2, I'm going to get these coordinates here. Let's see, this would be 2, -6, and this one would be 8, -6. And those are pretty easy to do. Just multiply each by 2. So I'm going to go ahead and graph that new triangle here. Alright, and you can see where now that I graphed these set of coordinates here, I've done that triangle in red, and it's now the same size as the triangle I'm trying to map to. Alright, so now I need to figure out, well, how am I going to get this triangle to map to be right on top of this triangle? Okay, well, I can do a reflection or a rotation or a translation, and I just have to figure out what combination of those it would be. Okay, so what I'm going to do is, I notice that it's oriented differently. This point Z is kind of pointing to the left here, to the negative side, and this point down here that would match up with it is pointing to the right. So I'm probably going to have to rotate it or flip it or reflect it at some point. So if I, maybe if I reflected it, alright, let's try a reflection first, and let's reflect this across the y-axis. I was going to say x-axis, but you know what, let's try this across the y-axis. So if I do that, I do a reflection across the y, and we'll put that right up here. Okay, I'm going to get a new set of coordinates for each one of these. So I'm just going to put those in there and see where we end up. Well, if I reflect over the y, I could use my rule. Alright, if you remember, reflecting over the y-axis, what it does is it changes the x-coordinate to be negative. Alright, so here's the points I'm going to end up with. -2, -4, -2, -6, and -8, -6. We've been doing that for a while now. Alright, so my new triangle would look like this. Alright, so first I dilated it. That took me to that one. Then I reflected it over the y-axis, and that takes me over to that one. Now, you can see that they're pointing the same way. They're oriented the same way. If I simply translate this straight up, I can transfer each one of these points to this position. So I'm just going to count here. I'm going to start here, and I'm going to count 1, 2, 3, 4. That gets me to the x-axis. 5, 6, 7, 8. Well, I'm just going to translate this every point on this triangle. I'm going to translate it straight up. What did I say? What was it? 8. Alright, so I'm going to do a translation. I'm not going to move it to the right or left, so that's going to be a 0 there. And I'm going to translate it in the positive 8 direction up. Alright, so this is going to give me a new set of coordinates, and they should match up with what x, y, and z are up here. So -2, -4, I'm going to add 8 to each one of the y coordinates. Alright, so -4, and I'm going to add 8, that gives me a positive 4. -6, I'm going to add 8, and that gives me a positive 2. And -8 stays the same. -6 again turns into a 2. Alright, and let's see. This should be point, actually I'm going to erase these right here. Let me get these arrows out of the way so I can put my points right in front here. So this should be point X, and if I go over here and count, -2, 1, 2, up 4, it's right on top of point X, and this should be point Y, which it is, -2, up 2, and this should be point Z, again, which it is, over -8 and up 2. So I did the dilation first, alright, and then I did a sequence of transformations, which again we call a congruence. But I did that sequence. First I did a reflection over the y-axis, and then I did a translation up 8. Alright, so those are the kind of things that I'm going to expect that you can tell me once we get them on the coordinate plane here. Alright, so that's about it. Thank you for watching once again. Have a good night, and we'll see you all tomorrow.